Have you ever wondered why some numbers can be broken into smaller multiplication parts while some numbers cannot? Think about the number 12. We can write 12 as 2 times 6 or 3 times 4. But what about 13? There is no smaller pair of natural numbers that multiplies to give 13, except 1 times 13. This simple difference takes us to one of the most important ideas in number theory, the Fundamental Theorem of Arithmetic. Before we understand the theorem, we need to clearly understand two types of numbers: prime numbers and composite numbers. A prime number is a natural number greater than 1 that has exactly two factors, 1 and itself. For example, 2, 3, 5, 7, 11, and 13 are prime numbers. Take 7. The only way to make 7 by multiplying natural numbers is 1 times 7, so 7 is prime. A composite number is also a natural number greater than 1, but it has more than two factors. It can be made by multiplying smaller natural numbers. For example, 4, 6, 8, 9, 10, and 12 are composite numbers. Take 12. It can be written as 2 times 6 and also as 3 times 4, so 12 is composite. Now, a very important point. The number 1 is neither prime nor composite. Why? A prime number must have exactly two factors, but 1 has only one factor, which is 1 itself, so 1 is a special number. Now, let us move to the main theorem. Imagine two students factorizing the number 60. One student starts with 6 times 10, then 6 becomes 2 times 3, and 10 becomes 2 times 5. So the final prime factors are 2 times 3 times 2 times 5. Another student starts with 2 times 30, then 30 becomes 3 times 10, and 10 becomes 2 times 5. Again, the final prime factors are 2 times 3 times 2 times 5. The path was different, but the final prime ingredients were the same. This is the beautiful idea behind the Fundamental Theorem of Arithmetic. The theorem says every composite number can be expressed as a product of prime numbers, and this factorization is unique, except for the order of the prime factors. Let us break that into simple parts. First, every composite number can be written as a product of primes. This process is called prime factorization. For example, 30 can be written as 2 times 3 times 5. All three factors are prime numbers. Second, this factorization is unique. That means each composite number has only one final set of prime factors. It's like the number's unique recipe, fingerprint, or DNA. Third, the order does not matter. For example, 2 times 3 times 5, 3 times 5 times 2, and 5 times 2 times 3 all mean the same prime factorization of 30. The ingredients are the same, only the order has changed. Usually, we write them from smallest to largest. Let us try one example using a factor tree. Suppose we want the prime factorization of 36. We can split 36 into 4 times 9, then 4 splits into 2 times 2, and 9 splits into 3 times 3. Now, every branch has ended in a prime number. So the prime factorization of 36 is 2 times 2 times 3 times 3. We can also write it as 2 squared times 3 squared. This is why prime numbers are called the building blocks of numbers. Composite numbers may look different, but when we break them fully, they are built from prime numbers. So in this lesson, we learned that prime numbers have exactly two factors, 1 and itself. Composite numbers have more than two factors and can be made by multiplying smaller natural numbers. The number 1 is neither prime nor composite. We also learned that every composite number has a unique prime factorization. The order may change, but the final set of prime factors does not change. This powerful idea is called the Fundamental Theorem of Arithmetic.